Right, so this is the second part of the organic synthesis question, synthesizing the compound Lipitor. We've already looked at how to make compound G, and I'm hoping this video will be quite quick, not because I'm running out of patience with synthesizing Lipitor, but it's 5 to 6. I'm getting quite hungry and could do with a bit of a snack. So let's get started. We've already done part A, so let's go to, surprisingly, part B. Here we go. And here we're taking an ester and we're deprotonating it by using a strong base. Now this produces a carbon nucleophile, which you can appreciate is extremely important for building up a carbon chain. If you've got a carbon with a lone pair of electrons on it, you can add that carbon attached to whatever else it's attached to something else. You can bind it to something else in a substitution reaction, and therefore you can build up a chain very, very quickly. So here we take a strong base. It's going to remove a proton, in other words an H+, and the only place where we could actually remove H+ from on here is here. So what you'll actually form is the ester, and we've lost H+ off here, so we've got CH2, and it will have a minus charge. It's going to have a lone pair of electrons. Now actually a more stable form of that is this compound here, but I'd be impressed if you came up with that, and that's because the lone pair of electrons here forms the double bond and breaks the pi bond here. However, just coming up with this and this structure is enough to answer the rest of the questions. So in this part of the question we are going to combine compound G, which we made earlier on, and I've drawn out compound G down here, with anion I, which we've just made, and here's anion I, which I've drawn out. You can see that when we combine the two, we lose C2H5OH. Now, if we look at G and I, where is C2H5O minus? And it's here. So we're going to lose that. So that nucleophile is going to bind here and substitute for this species in here. So J is going to be G written out, but instead of having that tail there, is going to have something which looks a little bit like that, or in fact is that, and that's going to be J. Now we're combining J with sodium borohydride. Now hopefully you know that sodium borohydride, like lithium aluminium hydride, is a reducing agent. And when I was doing this question earlier, I saw sodium borohydride and thought, right, brilliant, reducing agent, here's this nitrile group here, we're going to produce CH2, NH2 using that. And I went on to L and realised that actually that doesn't quite give us what we want in the next reaction. I was just sort of working on autopilot because so many of the Olympiad questions have reductions of these nitriles. So what else could the sodium borohydride reduce in our compound? Well, here you can see we've got a ketone functional group, and if we reduce a ketone we can produce a secondary alcohol. So that's exactly what we're going to make here. We've got OH, and the rest of the compound is as so. So we've turned the ketone here into that secondary alcohol, and that is in fact compound K. So we're going to take K and react it with this peculiar looking chemical there. That might be quite an eye-opener to some of you, and you might be thinking, what on earth are we going to do here? Well, again, like I advised in the last video, look ahead. it's clear that what I refer to as that peculiar chemical has something to do with that up there. And you can see we've got that, which mirrors that. So all that's going to happen in L is we're going to add this onto the top of our OHs here. So let's have a go at doing that. We'll keep our nitrile. And you'll hope you notice I'm getting a little bit better with the pen. And that's what we've made there. And that is in fact L. So just by looking ahead, we've worked out what the reaction is going to be. And then we're going to use hydrogen and a metal catalyst to turn our nitrile group into the amine that I was trying to do earlier on. So that will do that reaction there. And we'll keep going, so let's move on to the next slide. And here you can see we're building up an even bigger organic molecule, and this might appear a little bit daunting, but when you actually look at the Olympiad question itself, they do help you out. And everyone says, oh, the Olympiad's an absolute nightmare at times. And yeah, there are some tough questions, but there are some also absolute gimme questions on it. And if you're thinking, well, actually sometimes you only need 10, maybe 12 marks to get a medal, a question at this point says, draw out the structures of phenylamine and 4-fluorobenzaldehyde. So you have to be thinking at that point, well, that's an absolute gimme, and 2 very straightforward marks. So there's phenylamine, and helpfully I've drawn over one of the original molecules, and 4-fluorobenzaldehyde. So here's my benz, and there's my aldehyde group off it, and the fluorine group is at position 4 down there. So that's 2 marks straight off. And what's happening in this step, we've got the phenylamine down here combining with our molecule here. And we've got to produce something which is C12H15NO2. Now, as before, I do recommend looking ahead. And you can see we've got to produce this colourful molecule here. Now, you can see this looks rather similar to this area here, which means, it doesn't mean, but it suggests that this chain here might come from here. Now you can see that we've got our carbon-oxygen double bond, carbon-oxygen double bond, which matches here. Oh, and then on this molecule here, we've got OCH3. On this molecule here, we've got NH bonded to a phenyl group. So it doesn't quite match up, but oh, lo and behold, we've reacted N with phenylamine. So how will that happen? Well, phenylamine, nitrogen has a lone pair of electrons, and to be honest with you, off the top of my head, I don't know the exact mechanism for this, but that nitrogen will be extremely attracted to that carbon there. That carbon there is delta positive, extremely delta positive, because it's so close to 2 electronegative oxygens. It's therefore going to replace that species there. So and just to make things a little bit easier for myself, rather than drawing out the whole benzene ring, I'm going to write out the phenyl group as C6H5. Okay, so we've replaced that with our phenylamine, and that is compound O. Now you can see that a base has been used again, and remember 2 slides back we used a base to remove an H plus group, and have a look on this molecule O, where might we remove an H plus from? Now bear in mind we need to make this, we need to start building up from this carbon here, because that's going to come all the way down here. So that's going to be our attachment point. So that would be an excellent place to remove an H plus from. So anion P is exactly the same as that molecule there, except we've removed an H plus from there. So it's going to be minus, because you've taken away H plus, and therefore that is going to be an excellent nucleophile. So we're using what we had in, well, using the information that we were given previously in the question, and that's quite tricky to link those two things together, but maybe you spotted that. We're then going to add benzaldehyde. So here's benzaldehyde, okay, and it's got a carbon-oxygen double bond, and then to a hydrogen. And that lone pair of electrons here is going to be highly attracted to that delta plus site there, and the bond which breaks will be the pi bond attached there. So here's our C6H5 NH, and it does get quite time consuming drawing it all out. I'm hoping I haven't started too far across. Here's the rest of the blooming molecule. It takes ages, and it's very easy to make a slip. So we will attach that to where that carbon was. The bond had broken to the O, and there's another C6H5, which was this benzene ring here. Now that O doesn't look particularly good in terms of the chemistry. The lone pair of not the lone pair of electrons, the electrons in the pi bond had moved out to the O, so that should be O minus, but you've added a weak acid afterwards, so that means the O minus will bond to any H pluses which are floating around, so that will be OH, and you'll be feeling quite relieved because we're nearly there. That's Q, and we need to turn it into S, and you'd be thinking at this point, brilliant, we're almost there. 4-fluoroaldehyde is going to be our 4-fluorobenzaldehyde is going to be our final step. Here's 4-fluorobenzaldehyde on here, and you'd think, well, this OH is probably that carbon-oxygen double bond maybe at some point. It's in possibly the same position, possibly not. It's not. It's got nothing to do with that OH there. That and that are not the same oxygen. That oxygen has come from our 4-fluorobenzaldehyde. So we're losing H2O, so we're going to lose an OH here, and we're going to lose an H up here, and that will produce our final chemical S, so C6H5 NHO. So we're losing the OH, we're losing an H from here, that makes water, and obviously we need a bond here and a bond there to replace the things we've lost, so we form a carbon-carbon double bond, and then that will form T. And I'm rushing ever so slightly because I'm running out of time on the video.